Empty space is not empty at all. It is a seething, dynamic arena where the universe's most fundamental forces play out. This is the story beneath nothingness, and by the end, you will see the entire cosmos in a completely new light. We will uncover how the void can birth particles, bend the fabric of reality, and even hold the key to our own existence. What if the stillness around you is an illusion, concealing a quantum frenzy that dictates everything from the atom to the galaxy? How does it feel to realize that everything you know is built upon a foundation of nothing? Aristotle declared that nature abhors a vacuum, a belief that held sway for nearly 2,000 years. He argued that emptiness was a logical impossibility, a nothing that could not logically exist. Yet, in the shadows of this dominant view, other voices whispered a different truth. The ancient Greek thinker Democritus proposed that everything was composed of atoms and void, the ultimate something and the ultimate nothing, dancing together to create the richness of reality. This was not just an academic debate. It was a war of worldviews, fought with the only weapons they had, reason and observation. The Roman poet Lucretius, in his epic work on the nature of things, championed this atomic view, writing that the universe depends on a void, a boundless emptiness where matter can move and combine. He asked his readers to consider dust motes dancing in a sunbeam, a visible proof that unseen emptiness allows for motion. For centuries, these ideas simmered, challenging the Aristotelian orthodoxy that filled the cosmos with invisible substances. The battle lines were drawn: is space an absolute stage, or is it merely the relationships between objects? This philosophical clash erupted again in the 17th century with two intellectual giants, Isaac Newton and Gottfried Leibniz. Newton envisioned space as a vast, fixed container, an absolute and infinite void that existed independently of the objects within it. For him, this absolute space was the sensorium of God, a framework against which true motion could be measured. Leibniz, however, fiercely opposed this. He argued that space had no independent reality. It was only a set of relationships, a way of describing where things are in relation to one another. To him, the idea of a universe empty of everything but a single object was nonsense, because without other objects for reference, the concept of location becomes meaningless. This was not merely a theoretical dispute. It was a fundamental disagreement about the very fabric of reality. Was the stage itself real, or was the stage defined solely by the actors upon it? The decisive turn from philosophy to experiment came with a simple, powerful device, the air pump. In the 1650s, Otto von Guericke famously demonstrated the power of a vacuum with his Magdeburg hemispheres. He created a near-perfect vacuum inside two large copper bowls, and teams of horses could not pull them apart, held fast by the immense pressure of the outside atmosphere. Here was visceral, undeniable proof that a void could be created, that nature did not instantly rush in to fill it, and that this nothingness could exert a tremendous physical force. The air pump became a theater of demonstration, shattering Aristotelian dogma not with words, but with action. It paved the way for a new kind of science, one built on what could be measured and manipulated. This long, winding road of thought and experiment, from ancient arguments to public demonstrations, shows that our struggle to understand nothingness is as old as civilization itself. Every generation projects its own beliefs onto the void, and every generation is surprised by what it reflects back. These foundational battles set the stage for a revolution that would once again tear apart our understanding of the empty stage itself. A revolution led by a patent clerk who saw the universe in a new light. The trampoline sagging under a heavy weight is more than just an analogy. It is a fundamental rewrite of reality. Einstein's theory of general relativity did not just add to our knowledge, it shattered the very stage upon which Newton's universe was built. Space was no longer a rigid, absolute container. It became a flexible fabric, a dynamic entity that could be warped and curved by the mass and energy within it. What we feel as gravity is not a mysterious force reaching across emptiness, but the simple, inevitable result of moving through this curved geometry. A planet orbiting a star is not being pulled. It is following the straightest possible path through a distorted landscape. This was a monumental shift, turning passive nothingness into an active participant in the cosmic dance. The mathematics behind this can seem daunting, with objects called metric tensors describing how space-time is stretched and compressed. But you can feel the essence of it. Think of a grid painted on a stretched rubber sheet. Place a heavy ball in the center, and the grid lines bend inward. That distortion is gravity. The trampoline is not pulling on a smaller marble you roll past. The marble simply follows the curved path laid out for it. This relational view means that distance and time are not fixed, universal constants. They are malleable, changing depending on where you are and how you are moving. This radical idea received its first great confirmation in 1919, when astronomers observed starlight bending around the Sun during a total solar eclipse. The Sun's immense mass warped the spacetime around it, acting like a lens that deflected the light from distant stars. The empty space between the Sun and those stars was not nothing. It was a geometry that could steer light itself. Decades later, another stunning prediction of this dynamic fabric was confirmed: gravitational waves. When massive objects like black holes collide, they send ripples through the space-time fabric, vibrations that travel at the speed of light. The LIGO observatory detected these waves, essentially feeling the universe ring like a drum. This was not a wave in space, it was a wave of space itself, stretching and squeezing the very distances between objects. So we are left with a profound question. If emptiness can be warped, bent, and set vibrating, can we truly call it empty? It behaves more like a medium, a cosmic substance with its own properties and rules. This malleable fabric governs everything, from the stable orbit of the Earth to the relentless expansion of the entire universe. Yet, just as we come to grips with this new, dynamic void, an even stranger truth awaits in the realm of the impossibly small. Yet even this dynamic fabric of spacetime is not the final word on emptiness. Beneath the smooth curves of relativity lies a far more chaotic and restless realm. The quantum vacuum is not a still and silent void, but a seething foam of potential. Picture a calm sea on a windless day. Its surface appears perfectly flat and serene. But if you could look at the smallest possible scale, you would see that same surface constantly erupting with tiny bubbles, forming and popping in an unending frenzy. This is the essence of the quantum world. The vacuum is not empty. It is the lowest possible energy state, a state that is still wildly active. This radical idea was born from the minds of pioneers like Paul Dirac and Werner Heisenberg, who developed quantum field theory. They showed us that the fields which fill all of space can never be completely turned off. They are always jittering, always fluctuating. This is a direct consequence of the Heisenberg uncertainty principle, a cornerstone of quantum mechanics. This principle tells us that for incredibly brief moments, energy can be borrowed from nowhere, so long as it is paid back almost instantly. This temporary loan allows for the spontaneous creation of particle and antiparticle pairs, virtual particles that flicker into existence and then annihilate each other before the universe can notice the debt. These are not mere mathematical tricks. They have real, measurable effects. The Dutch physicist Hendrik Casimir predicted that if you place two uncharged, perfectly smooth metal plates extremely close together in a vacuum, they would be pushed together by a mysterious force. The reason is that the gap between the plates is so small that only certain wavelengths of these quantum fluctuations can fit inside. Outside the plates, all wavelengths are possible. The greater pressure from the outside forces the plates together. This Casimir effect has been experimentally confirmed, a tangible pull generated by the restless energy of apparent nothingness. This activity also shapes the forces we know. The physicist Richard Feynman beautifully explained that the electromagnetic force between two electrons is actually mediated by a constant, frantic exchange of these virtual particles. The quiet emptiness is, in fact, a bustling marketplace of unseen transactions. In powerful particle accelerators, we can give these virtual particles a permanent existence. By slamming real particles together with immense energy, we deliver a kick so powerful that the vacuum itself responds, making the fleeting virtual particles real, literally pulling matter out of the void. So what does this mean for our understanding of reality? If the very foundation of space is this unstable, energetic sea, can anything truly be considered solid or permanent? The atoms that make up your body are mostly empty space, held together by forces born from this quantum static. The stability you feel is a magnificent, large-scale illusion. Just as we begin to accept this frantic quantum vacuum as the true nature of emptiness, we must confront its most staggering consequence, a force that emerges from this void to dictate the ultimate fate of the entire cosmos. That frantic quantum sea holds a shocking secret, a pressure within the vacuum itself that is now tearing the cosmos apart. The discovery of dark energy began not with a grand theory, but with patient observations of dying stars. In the late 1990s, two independent teams, one led by Saul Perlmutter, were studying a specific type of stellar explosion, a supernova, to measure how the universe's expansion has changed over time. Everyone expected to find that the gravity of all the matter in the cosmos was putting a brake on this expansion, gradually slowing it down. The data revealed the opposite. The most distant supernova were fainter than they should have been, meaning they were farther away than anyone predicted. The expansion of the universe is not slowing down, it is accelerating. It is as if you tossed a ball into the air and watched it fly upward faster and faster, defying gravity itself. This stunning revelation earned Perlmutter and his colleagues the Nobel Prize and forced cosmologists to confront a profound truth. Empty space is not inert. It contains a mysterious repulsive force, a kind of anti-gravity that is pushing galaxies away from each other at an ever-increasing rate. This is dark energy. It now makes up about 68% of the entire energy density of the universe, completely dominating everything we can see and touch. The leading candidate for this mysterious force is a concept Einstein himself stumbled upon decades earlier, the cosmological constant. He initially introduced this mathematical fudge factor into his equations of general relativity to achieve a static universe, a notion he later called his greatest blunder. But in the face of cosmic acceleration, the cosmological constant has been dramatically revived. It represents a constant energy density inherent to the vacuum of space itself. Think of it as a property of nothingness, a steady pressure that does not dilute as the universe expands. As more space comes into existence, more of this repulsive energy appears with it, leading to a runaway process of expansion. This is not the only explanation, however. Some theories propose a dynamic field called quintessence, a kind of fifth, fundamental force that could change over time. Yet the simplest model, the cosmological constant, aligns remarkably well with other independent evidence, like the precise patterns seen in the cosmic microwave background radiation, the faint afterglow of the Big Bang. The implications for our cosmic fate are staggering. If dark energy continues to dominate, as all evidence suggests it will, the universe is headed for a cold and lonely end known as the Big Freeze. Over trillions of years, the acceleration will pull all other galaxies beyond our cosmic horizon. The night sky will go dark. Our own Milky Way will be left isolated in an ever-expanding void, and the universe will become a vast, cold, and increasingly empty silence. So we are left with the ultimate question: why does nothingness have this energy? Why does the vacuum, the very definition of emptiness, push the universe apart? This force, born from the quantum void, is now the master of cosmic destiny. And to understand how it seized control, we must rewind time to the universe's first fleeting moments, to an epoch when the void unleashed an expansion so violent it defies all comparison. This primordial void did not remain quiet for long. Within a fraction of a second after the beginning, the universe was seized by a force of exponential growth so violent it makes the current expansion seem placid. This is the theory of cosmic inflation, a moment when the cosmos ballooned from a subatomic speck to a volume far larger than our entire observable universe. Alan Guth, one of its key architects, described it as the ultimate free lunch, a period driven by a peculiar vacuum-like energy field that forced space itself to stretch at an unimaginable rate. This explosive growth solves profound puzzles. Consider the horizon problem. We look in opposite directions of the sky and see the cosmic microwave background radiation has the same temperature. Yet these regions were too far apart for light, and thus heat, to have ever traveled between them. How did they reach a thermal equilibrium? Inflation provides the answer. Before the rapid expansion, the entire observable universe was a tiny, connected patch that had ample time to even out its temperature. Then, inflation blew this tiny, uniform region up to a colossal size, preserving its sameness across the vast cosmic distances we see today. It also explains why the fabric of space appears so flat. Just as inflating a balloon to an enormous size makes its surface seem flatter and flatter from our local perspective. The engine for this incredible event was a hypothetical field dubbed the inflaton. Think of it as a field of energy that temporarily behaved like a supercharged version of dark energy, providing a relentless, repulsive push. While this inflaton field was dominant, the universe expanded exponentially, doubling in size over and over again in intervals of time so brief they are almost meaningless. But this field was unstable. Eventually it decayed like a ball slowly rolling down a hill. The tremendous energy stored in the inflaton field was then released in a grand burst, flooding the universe with particles and radiation, an event we now call the Hot Big Bang. Inflation did not just create a smooth, vast universe. It also planted the seeds for all future structure. The quantum foam of the primordial void was still seething, and these tiny fluctuations in the inflaton field were stretched to enormous sizes by the rapid expansion. These ripples in nothingness became the blueprint for everything. The slightly denser regions, where a little more energy had pooled, would later, through gravity, attract more matter. These became the gravitational wells that eventually collapsed to form galaxies, stars, and planets. The entire cosmic web, from the largest cluster to the smallest star, owes its origin to these microscopic quantum jitters. We have seen the evidence for this written in the oldest light we can see. Satellites like Planck have mapped the cosmic microwave background with exquisite precision, and the tiny temperature variations they detect, the hot and cold spots, match the predictions of inflation perfectly. They are the fossilized imprint of those quantum seeds, the signature of a restless void giving birth to a structured cosmos. This leads to a staggering implication. If the inflaton field could undergo such a transition once, could it happen elsewhere or at other times? Many physicists now speculate that inflation may be eternal, ceasing in some regions to create bubble universes like our own, while continuing forever in others, generating a vast, perhaps infinite, multiverse. So we are left to ponder a humbling thought. The grand tapestry of the cosmos, with its billions of galaxies, may have its origins not in a singular fireball, but in the subtle, quantum vibrations of a near nothingness. As these seeds grew into the universe we know, another mysterious process was weaving invisible threads across the expanding void. connecting it in ways that challenge our deepest notions of space and time. This quantum connection defies every intuition about distance. Two particles born from the same event can become entangled, their fates linked in a way that makes a mockery of the space between them. It is as if you had two magical coins, one given to a friend who boards a rocket to a distant galaxy. The moment you flip your coin and see it land heads, you know with absolute certainty that theirs has landed tails instantaneously across that vast cosmic gulf. This is not science fiction, it is a fundamental property of our quantum world, and it left even Albert Einstein deeply unsettled. He derided it as spooky action at a distance, a phrase that perfectly captures the unease that comes from an effect that seems to travel faster than light. Einstein, along with colleagues Boris Podolsky and Nathan Rosen, highlighted the bizarre implications through a thought experiment now called the EPR Paradox. They argued that if quantum mechanics were correct, then measuring one particle would instantly dictate the state of its entangled partner, no matter how far apart they were. To them, this implied that quantum theory was incomplete, that there must be some hidden variables, some deeper layer of reality that we simply could not see. For decades, this remained a philosophical debate, a clash of worldviews between giants like Einstein and Niels Bohr. Then, in the 1960s, a brilliant physicist named John Bell found a way to translate the argument into a real, testable experiment. Bell's theorem provided a mathematical way to distinguish between a universe with local hidden variables, which Einstein would have preferred, and the truly spooky quantum world. He proposed that if you could measure many pairs of entangled particles, their correlations would fall within a certain limit if hidden variables were at work. If the correlations exceeded that limit, then spooky action was real. When experiments were finally conducted, the results were unequivocal. The quantum correlations won. Measuring the spin or polarization of one entangled photon does indeed instantly determine the state of its partner. This does not allow for faster-than-light communication, a crucial point. You cannot use this to send a message because the outcome of your measurement is random. You only know what your partner got after the fact, when you compare notes at the speed of light or slower. But the connection itself is immediate. The vacuum is not a barrier that separates these particles. It is a medium that supports their profound, instantaneous link. This non-local connection is not just a laboratory curiosity. It is the engine of emerging technologies. In quantum cryptography, the act of measuring an entangled particle inevitably disturbs it. This means that if a spy tries to eavesdrop on a quantum-encrypted message, the very act of listening introduces errors that the legitimate users can immediately detect, guaranteeing perfect security. In quantum computing, entangled qubits can represent a vast number of possibilities simultaneously, allowing them to perform complex calculations in parallel that would take a classical computer millennia. These particles, talking to each other across any distance, force us to ask a radical question. Is the space between them real, or is it a kind of illusion? If two things can be so intimately connected without any signal passing through the space that separates them, then what is the purpose of that space? It suggests that our perception of separation, of distinct objects in a vast emptiness, might be a kind of projection from a deeper, more fundamental layer of reality where everything is connected. This very idea leads us to one of the most mind-bending concepts in all of physics, the notion that our three-dimensional world, with all its volume and emptiness, might be nothing more than a hologram. That profound connection of quantum entanglement forces us to question the very reality of space. Could the three-dimensional void we perceive be nothing more than a magnificent illusion? The holographic principle offers a radical answer, suggesting that our universe, in all its volume and emptiness, is a projection from a distant, two-dimensional surface. Think of a three-dimensional movie, where the depth and action you experience are all encoded on a flat screen. This is not just a metaphor. It is a serious theory, born from the deepest puzzles of black hole physics. Physicists Gerard T. Hooft and Leonard Susskind realized that the maximum amount of information you can store inside any region of space is not proportional to its volume, as you might expect, but to the area of its boundary. A black hole, the ultimate trap for information, obeys this exact rule. Its entropy, a measure of its information content, is defined by the surface area of its event horizon, not the vast volume hidden within. This was a profound clue. It hinted that perhaps all the information needed to describe everything inside a volume, every star, every planet, every one of us, could be painted like a cosmic barcode on its outer surface. This is the essence of the holographic principle. Our reality, with its three spatial dimensions, might be a holographic projection from a two-dimensional film of quantum information residing at the very edge of the observable universe. The void is not empty. It is a shimmering mirage emerging from a deeper, more fundamental layer. This idea finds a precise mathematical home in a concept from string theory known as the AD/CFT correspondence. It proposes a perfect duality. A universe with gravity, like ours, described by a certain geometry, is completely equivalent to a quantum field theory, a description of particles and forces that lives on its boundary. In this picture, the force of gravity and the very fabric of spacetime are not fundamental. They emerge from the complex, entangled interactions of countless quantum bits on the lower dimensional boundary. The smooth, curved geometry of space is like a collective hallucination, a large-scale effect of this underlying quantum code. This provides a stunning potential resolution to the black hole information paradox. If a star collapses into a black hole, all the information about that star is not lost inside the singularity, as classical physics suggested. Instead, that information remains safely stored, scrambled but preserved, on the event horizon's two-dimensional surface. When the black hole evaporates through Hawking radiation, that information can, in principle, be retrieved. The holographic universe saves information from oblivion. But how could we ever test such an abstract idea? Scientists are looking for subtle fingerprints in the oldest light we can see, the cosmic microwave background. If space is truly emergent from a quantum information network, there might be tiny, specific anomalies in this radiation, a kind of pixelation or noise that betrays the underlying digital nature of reality. Other experiments, like precise studies of quantum entanglement in the vacuum itself, might reveal the granularity of spacetime. So what does this mean for the nature of time? If space is an emergent property, then time itself might also be a derivative concept, a story that unfolds from the timeless, churning interactions of the quantum vacuum. We are left with a humbling and awe-inspiring possibility. The vast, three-dimensional cosmos, with its galaxies swirling in the darkness, may be the grandest illusion of all. The true reality is a flatter, stranger, more information-dense place. And the emptiness we have been studying is the magnificent projection of that deeper truth. This journey into the void has revealed layer after layer of complexity, from a dynamic fabric to a quantum sea to a cosmic projection. But to truly grasp the significance of this emergent reality, we must ask a more personal question. The relentless flow of time, like sand through an hourglass, seems an undeniable fact of our existence. Yet this arrow of time, pointing always from past to future, finds its ultimate source not in the ticking of a clock, but in the peculiar order of the primordial void. Physicists like Sean Carroll point to a concept called entropy, the measure of a system's disorder, as the engine of time's arrow. The universe is constantly moving from a state of lower entropy to higher entropy, from order to disorder, and this progression is what gives us a past distinct from a future. But why did the universe start with such incredibly low entropy in the first place? The answer lies in the aftermath of cosmic inflation. The inflatoned field decayed, releasing its energy and creating a universe that was remarkably smooth, uniform, and therefore in a state of very low entropy. This was the ultimate wound-up spring. The cosmic microwave background is our fossilized evidence of this initial order, a snapshot of a young cosmos with only tiny temperature variations. From that pristine starting point, the universe could only become more disordered over time. Gravity played a crucial role in this process. Those tiny quantum fluctuations from the vacuum, stretched by inflation, became the seeds for structure. Slightly denser regions began to pull in more matter through gravity, eventually collapsing into galaxies and stars. This might sound like things are becoming more ordered, but in thermodynamic terms, it is a massive increase in entropy. A smooth, featureless gas has lower entropy than a universe clumped into hot stars and cold, dark space. The formation of a star is a local act of creation paid for by a vast, cosmic debt of increasing disorder. This deep connection between the early vacuum and the arrow of time leads to some bizarre thought experiments, like the Boltzmann-Brane Paradox. This paradox suggests that in a vast, eternal universe, random fluctuations could spontaneously assemble a fully formed, conscious brain out of the chaos, complete with false memories of a past. It is far more probable for a single brain to fluctuate into existence than an entire ordered universe. The fact that we see a vast, coherent cosmos around us, and are not just fleeting Boltzmann brains, is powerful evidence that our universe began in a very special, low-entropy state, set by the conditions of the quantum vacuum. Even black holes, the ultimate sinks of order, are central to this story. The Bekenstein-Hawking formula shows that a black hole's entropy is proportional to the surface area of its event horizon, not its volume. This was a monumental clue that led toward the holographic principle, suggesting that information and disorder are fundamentally linked to boundaries. It implies that the flow of time itself, which is inextricably tied to increasing entropy, might not be a fundamental feature of reality. Perhaps time is an emergent property, a story that unfolds from the timeless, churning interactions of quantum information at the universe's edge. So when you feel the relentless march of seconds, minutes, and years, you are feeling a direct consequence of that ancient, smooth vacuum. Your very existence, your memories, and your sense of a linear past are all gifts from a nothingness that began with a very specific kind of order. This profound link between time and the void forces us to confront an even more intimate connection, one that touches the very mass of the particles that constitute you and everything you see. That cosmic void, which dictates the flow of time itself, is also responsible for the very substance of your being. Your mass, the property that gives you weight and solidity, is not an innate quality of matter. It is a gift from an invisible field that fills every corner of emptiness. Think of a room crowded with admirers. A famous person trying to cross that room would move slowly, hindered by constant handshakes and conversations. An unknown individual could glide through effortlessly. This is the essence of the Higgs mechanism. The entire universe is permeated by the Higgs field, an invisible energy field that acts like a cosmic molasses. Particles that interact strongly with this field, like the top quark, acquire a great deal of mass and move sluggishly. Particles that barely interact, like photons of light, have no mass at all and zip through the void at the ultimate speed limit. This elegant idea was proposed independently by several physicists, including Peter Higgs, and became known as the Braut-Englert-Higgs theory. It describes a process called spontaneous symmetry breaking that occurred in the early universe. Just after the Big Bang, the Higgs field was zero everywhere, a state of perfect symmetry. But as the universe cooled, this became an unstable arrangement, like a pencil balanced perfectly on its tip. The field settled into a new, stable state with a non-zero value everywhere. This is the vacuum we inhabit today, a nothingness that is forever switched on. The Higgs boson, the particle famously discovered at CERN in 2012, is crucial to this picture. It is not the field itself, but a localized ripple or excitation within it. Detecting this boson was like feeling the texture of the molasses. The immense particle collisions at the Large Hadron Collider provided enough energy to jostle the Higgs field, making it slosh and reveal its quantum. This confirmation was a monumental triumph, validating decades of theoretical work and showing that our most fundamental properties are bestowed by the silent, empty space around us. Without this field, electrons would have no mass and could not be captured into orbits around atomic nuclei. There would be no atoms, no chemistry, no planets, and no people. The structure of our reality hinges on this interaction with the void. This discovery forces us to wonder, if one such field fills the vacuum giving mass to particles, could other, undiscovered fields be lurking in the emptiness, perhaps governing other mysterious properties of our universe? The void is not a stage for the actors of matter. It is the director that hands them their scripts, defining their roles in the cosmic play. This invisible orchestra never falls silent. Its instruments are the quantum fields that fill every point in space, with each fundamental particle, from the humble electron to the massless photon, representing a different note in an eternal symphony. Quantum field theory is the sheet music for this cosmic performance, a framework developed by visionaries like Richard Feynman and Julian Schwinger that redefines the very idea of emptiness. They revealed that what we perceive as a void is in fact a plenum, a space saturated with fields. The particles we think of as solid, permanent things are merely fleeting excitations of these fields, like temporary ripples on a vast, deep ocean. The vacuum is simply the ground state, the quietest these fields can be, but even this baseline hums with immense activity. The mathematics describing this symphony is known as the Lagrangian, a powerful equation that encapsulates the total energy of the fields and dictates how they interact and evolve. This formalism shows us that forces are not mysterious pulls at a distance, but are mediated by the exchange of force carriers. In quantum electrodynamics, for instance, the electromagnetic force between two electrons is the result of them constantly tossing photons, the carrier of that force, back and forth. This frantic exchange is what creates the repulsion we measure. But this beautiful picture initially contained a terrifying flaw: infinities. When physicists tried to calculate the effects of the vacuum's quantum fluctuations, their equations would often spit out infinite, nonsensical answers. The solution was a brilliant mathematical technique called renormalization. Think of it as a cosmic accounting system. It acknowledges that the properties we measure, like a particle's mass or charge, are not its bare, isolated values, but the sum total of the particle and its constant interaction with the vacuum's seething energy. Renormalization provides a systematic way to subtract these infinite vacuum contributions, leaving behind the finite, measurable values we observe in experiments. This is not just a mathematical trick. It has real, observable consequences. In quantum electrodynamics, a process called vacuum polarization occurs. The electric charge of a particle, like an electron, is not a fixed number in a true void. Instead, the electron is constantly surrounded by a cloud of virtual particle-antiparticle pairs popping in and out of the vacuum. This cloud polarizes, effectively screening the electron's true charge. What we measure as its charge is this screened, diluted value. The emptiness is not passive, it actively dresses every particle, modifying the very constants we once thought were immutable. So what does this mean for our reality? If everything is merely a vibration in an underlying field, is the solidity of the world around us just a collective illusion, a persistent pattern in this cosmic hum? This field-filled view of the vacuum is one of the most successful theories ever devised, yet it leads directly to one of the most profound failures in modern physics. The same quantum field theory that so perfectly describes particles and forces predicts a vacuum energy of such staggering magnitude that it should have torn the universe apart in its first instant. The calculated value and the observed value of this energy differ by a factor of 1 followed by 120 zeros, the worst mismatch between theory and experiment in the entire history of science. This is the cosmological constant problem, a screaming paradox born from our deepest understanding of nothingness. That screaming paradox echoes through every calculation of the void. Quantum field theory, our most precise description of the particle world, allows us to calculate the energy of a perfect vacuum. We sum up all the zero-point energy, the relentless jittering of every quantum field at its lowest possible state. The result is a number of such staggering magnitude it should have curved the fabric of spacetime into a tight knot, instantly collapsing the universe or blowing it apart before a single atom could form. The theoretical prediction and the observed value of the vacuum energy differ by a factor of 1 followed by 120 zeros. This is not a small error. It is the most catastrophic failure of prediction in the entire history of science. The physicist Steven Weinberg noted that this cosmological constant problem is a crisis, a clear sign that our understanding of nothingness is fundamentally, profoundly wrong. The two pillars of modern physics, quantum theory and general relativity, are at war over the energy of empty space. One tells us the void should be bursting with power. The other observes a whisper-quiet hush. How can we reconcile this? One proposed solution involves a principle called supersymmetry. This elegant idea posits that for every known particle of matter, there exists a superpartner particle of force, and vice versa. If this symmetry were perfect, the contributions of these particle pairs to the vacuum energy would perfectly cancel each other out, leaving a net energy of zero. The problem is, we have found no evidence for these superpartners in our particle colliders. Supersymmetry, if it exists, must be a broken symmetry, and the cancellation is imperfect, leaving us back with our enormous discrepancy. Another, more controversial, explanation invokes the Anthropic Principle and the Multiverse. If inflation is eternal, generating a vast multiverse of bubble universes, then each one could have a different, random value for the vacuum energy. In almost all of these universes, the energy would be too large, leading to instant collapse or rapid, sterile expansion. Only in very rare bubbles, like our own, is the value small enough to allow for the slow gravitational collapse that forms galaxies, stars, planets, and ultimately, life. In this view, we do not observe a special void. We simply inhabit one of the few universes where the void is quiet enough for us to exist. This is not an explanation in the traditional sense. It is a form of cosmic natural selection. The philosophical implications are dizzying. Does the universe need observers to give it meaning? Or is our existence merely a fortunate accident in a vast cosmic lottery? This fine-tuning is so exquisite it demands an answer. Perhaps the solution lies in a theory that seamlessly unites gravity with quantum mechanics, a theory of quantum gravity where spacetime itself is revealed to be discrete, woven from tiny, fundamental grains. In such a framework, the infinite sums that currently plague our calculations would be naturally tamed, and the true, small energy of the vacuum would emerge from first principles. The enigma of the cosmological constant is not just a technical puzzle for physicists. It is a direct challenge to our story of reality. It forces us to ask if the void itself is trying to tell us something, if its unnatural silence is a clue to a deeper structure waiting to be uncovered. And this is not merely a question for telescopes and cosmic observation, for the answers may be found much closer to home, in the quiet hum of laboratory experiments designed to listen to the whispers of the vacuum. These subtle whispers of the void are not just theoretical curiosities. We can actually hear them in laboratory experiments of astonishing precision. Scientists use instruments so sensitive they can detect the faint pressure exerted by nothingness itself. The classic demonstration is the Casimir effect, where two incredibly smooth, uncharged metal plates are placed mere nanometers apart in a perfect vacuum. In that narrow gap, only certain wavelengths of the quantum field's fluctuating virtual particles can fit. Outside the plates, all wavelengths are possible. This creates an imbalance, a greater pressure from the outside that pushes the plates together with a measurable force. It is a tangible pull generated by the restless energy of the vacuum, a direct observation of quantum froth made real. This phenomenon was predicted by the Dutch physicist Hendrik Casimir, a brilliant mind who saw the bridge between abstract theory and concrete measurement. Modern science has taken this much further, crafting nanostructures and micro-electromechanical systems, or MEMS, that can probe the vacuum's properties with ever greater control. Another powerful technique is called cavity quantum electrodynamics. Here, scientists use superconducting mirrors to create a tiny cavity that traps light. By confining photons in this way, they can amplify the subtle interactions between light and the vacuum's virtual particles, essentially making the whispers of nothingness louder and easier to study. A key advancement in this field is quantum squeezing. The Heisenberg uncertainty principle dictates a fundamental fuzziness in quantum measurements, a kind of inherent noise. But scientists have learned to squeeze this uncertainty, redistributing it so that one property can be measured with extreme precision, even if another becomes less certain. This allows them to reduce the measurement noise that comes from the vacuum's own fluctuations, letting them listen more clearly to the signal they are after. One of the earliest and most profound confirmations of this quantum activity is the Lamb shift. In the hydrogen atom, the electron orbiting the proton should have a very specific energy level according to the simplest quantum model. But in the 1940s, Willis Lamb and his colleague Robert Rutherford discovered a tiny shift in that energy. The reason is the vacuum itself. The electron is constantly buffeted by the appearance and disappearance of virtual particles, which slightly alters its orbit and its energy. This minuscule shift, predicted by the developing theory of quantum electrodynamics, was a spectacular victory, proving that even the simplest atom is in constant, silent conversation with the empty space around it. So where do these experimental probes lead us next? Could future, even more sensitive versions of these experiments finally detect the ripples of spacetime known as gravitons, or perhaps measure the local influence of dark energy? These are the bold frontiers of vacuum exploration. By pushing our instruments to their absolute limits, we are not just testing theories, we are learning to converse with the void. And this hands-on interrogation of nothingness is now guiding theorists toward possibilities that stretch the very definition of reality, suggesting that the empty space we perceive might be hiding entire dimensions folded within its fabric. The vacuum's deepest whispers might be echoing in dimensions we cannot see. String theory dares to suggest that the fundamental building blocks of reality are not point-like particles, but unimaginably tiny, vibrating loops of energy. Each distinct vibration of these strings produces a different note in the cosmic symphony, creating the entire zoo of particles and forces we observe, from the electron to the graviton, the hypothetical carrier of gravity. This elegant idea, championed by thinkers like Edward Witten, offers a breathtaking possibility for unifying all the forces of nature, including gravity, into a single, coherent framework. To make the mathematics of these vibrating strings work, the theory requires more than the three spatial dimensions we experience. It demands extra dimensions, perhaps 6 or 7 of them, all curled up into shapes so fantastically small that they escape our notice. Witten has described how these dimensions could be curled at the Planck scale, a size a billion trillion times smaller than an atom. Our entire observable universe, with its vast, seemingly empty space, might be threaded through with this hidden, intricate geometry. The specific shapes that define these extra dimensions are known as Calabi-Yau manifolds. Picture a shape of breathtaking complexity, a multi-dimensional jewel with holes and handles, a labyrinth folded upon itself in ways the human mind can scarcely visualize. The precise form of this Calabi-Yau manifold determines the properties of our vacuum, dictating how strings vibrate and thus what kinds of particles and forces emerge into our macroscopic world. This leads to a profound and unsettling implication: the string theory landscape. Rather than one unique vacuum, there could be a staggering number of possible Calabi-Yau shapes, each corresponding to a different universe with its own laws of physics. We may not live in a uniquely tuned cosmos, but simply in one where the vacuum's properties, set by these hidden dimensions, accidentally allow for atoms, stars, and life. This speculative leap connects directly to the Anthropic Principle, the idea that the constants of nature are what they are because, in a vast multiverse of possibilities, we could only arise in a universe that permits our existence. A compelling extension of this idea is Brane Cosmology. In this picture, our entire three-dimensional universe could be a membrane or a brane, floating within a higher dimensional space called the bulk. The particles and forces we know might be stuck to our brain, unable to leave, which is why we perceive only three spatial dimensions. But gravity, the weakest and most enigmatic force, could be different. It might be able to leak off our brain and dissipate into the higher dimensional void. This could explain why gravity is so incredibly feeble compared to the other forces, its strength diluted as it spreads into these unseen dimensions. So the next time you look up at the night sky, consider that the emptiness you see might be an illusion of scale. What appears to be a vast, three-dimensional void could be a thin slice of a much richer, higher-dimensional reality. A reality where the very fabric of space is woven from tiny, vibrating strings whose hidden harmonies compose the symphony of existence. This delicate balance is terrifyingly precise. A universe where the vacuum energy was just slightly higher would have seen its expansion accelerate with such violence that no galaxies could ever have formed, scattering matter into a thin, sterile mist. Conversely, a value even a little lower would have allowed gravity to win too quickly, causing the entire cosmos to collapse back in on itself in a swift, fiery crunch. In either scenario, no stars, no planets, and certainly no life could ever arise. The fact that we are here to ponder the void means we live in a universe where this value is not just small, but exquisitely, improbably tuned. This is the core of the Anthropic Principle. The idea that the universe we observe must be compatible with the existence of conscious life that observes it. The vacuum itself appears to be fine-tuned for our existence. The renowned cosmologist Martin Rees has eloquently framed this by pointing to several cosmic numbers, with the cosmological constant being paramount among them. He argues that in a multiverse, a vast collection of universes each with different physical laws and vacuum energies, it is no surprise that we find ourselves in one of the rare, bio-friendly bubbles where the numbers just happen to be right. This idea comes in two forms. The weak Anthropic Principle is a simple statement of selection bias. We could not possibly observe a universe that did not allow for observers. The strong Anthropic Principle goes further, suggesting that the universe must have properties that inevitably lead to life, which some interpret as pointing toward purpose or design. This fine-tuning is starkly illustrated by the dark energy density. Its observed value is around 120 orders of magnitude smaller than what quantum field theory predicts. It is a number so close to zero, yet not quite zero, that it seems to shout of something deeply significant. Why is the energy of nothingness so perfectly calibrated to allow for the slow, graceful dance of galaxy formation? The anthropic reasoning within a multiverse offers one answer. In an infinite array of universes, every possible value will occur somewhere, and we simply inhabit a lucky one. Yet this explanation is not without its fierce critics. A major objection is that the multiverse concept, while compelling, currently lacks falsifiability. How could we ever test for the existence of other universes with different vacuum states? Without the possibility of experimental proof, some argue it veers into the realm of philosophy rather than science. Others find the idea of a near infinite number of unobservable universes to be an unsatisfying, almost magical solution to a profound physical problem. Are we simply explaining one mystery by invoking an even greater one? Alternatives do exist, such as the string theory landscape, which provides a potential mechanism for this cosmic variation. The myriad ways to curl up the extra dimensions of string theory could generate a colossal landscape of possible vacua, each with its own laws and constants. Our universe would then be just one leaf in an infinite forest. But this still leaves us with the haunting question of why this particular leaf. Is our existence here a matter of pure, blind chance? Or does the specific silence of our vacuum hint at a deeper, yet undiscovered, physical principle that naturally forces the cosmological constant to be zero? This fine-tuning of nothingness leads our gaze toward the most extreme environments in the cosmos, where the vacuum is not quiet and accommodating, but is stretched and stressed to its absolute breaking point. At the edge of a black hole, the vacuum itself is torn in two. This is the realm of Hawking radiation, a phenomenon where the void does not just whisper, it screams. Stephen Hawking made his most startling prediction by applying quantum rules to the terrifying gravity near an event horizon. He realized that the vacuum's inherent fluctuations are not cancelled here, but amplified by the black hole's immense gravitational field. A virtual particle pair, constantly blinking in and out of existence, can find itself split apart. One particle falls across the event horizon, forever lost, while its partner escapes into space, carrying away a tiny bit of the black hole's energy. To an outside observer, this stream of escaping particles looks exactly like thermal radiation, a faint heat glow emanating from the black hole's edge. Hawking himself described it with elegant simplicity, saying that black holes are not so black after all. They have a temperature, and they slowly evaporate over astronomical timescales. This was a monumental connection, linking the three great pillars of physics, gravity, quantum mechanics, and thermodynamics, into a single, breathtaking picture. The emptiness of space is the medium through which this entire process operates. The mathematical engine behind this is quantum field theory in curved spacetime. In the flat, calm space far from any massive object, the vacuum has a straightforward definition. But near a black hole, spacetime is so warped that this definition breaks down. What one observer sees as empty space, another observer, falling into the black hole, would see as a blistering storm of real particles. This relativity of particle creation is the heart of Hawking's calculation. The event horizon acts as a one-way membrane that irrevocably separates the virtual particle pair, promoting them from fleeting ghosts to permanent residents of reality. This elegant solution, however, created one of the most persistent puzzles in modern physics, the black hole information paradox. Quantum mechanics states that information is never truly lost. If you burn a book, in principle, you could collect all the smoke and ashes and reconstruct its every word. But if you throw that book into a black hole, and the black hole subsequently evaporates through Hawking radiation, what happens to the information? The radiation appears to be purely random and thermal, containing no trace of what fell in. The information seems to have vanished from our universe, violating a core quantum principle called unitarity. This paradox has spawned fierce debates and radical ideas. One of the most dramatic is the firewall paradox. It suggests that to preserve the laws of quantum mechanics, the event horizon cannot be the smooth spacetime gateway general relativity describes. Instead, it must be a wall of searing energy, a literal firewall born from the amplified vacuum fluctuations that would instantly incinerate anything crossing it. This presents a stark choice. Either our understanding of Einstein's gravity is wrong at the horizon, or our understanding of quantum mechanics is wrong. Most physicists believe the answer lies in a more subtle resolution, perhaps where the information is not lost, but is encoded in the Hawking radiation itself in a complex, scrambled form, or is stored on the event horizon's surface as the holographic principle suggests. So, is a black hole the ultimate vacuum? It is the closest thing to absolute nothingness our universe allows, a region from which even the vacuum's virtual particles can be stolen. Yet, in its profound emptiness, it radiates, it heats up, and it potentially stores the entire history of everything it has consumed. The fate of information falling into a black hole forces us to question the very nature of reality at its most fundamental level. And if we could peer into that darkness at the smallest possible scale, we would find that the fabric of spacetime is not smooth, but a chaotic, bubbling foam. The smooth stage of spacetime dissolves into a chaotic froth at the very bottom of reality. At the unimaginably small Planck scale, a distance of 10 to the negative 35th meters, the void is not a serene emptiness but a turbulent sea of virtual black holes and wormholes, constantly bubbling in and out of existence. This is spacetime foam, a concept pioneered by the physicist John Wheeler, who saw it as the inevitable meeting point of general relativity and quantum mechanics. In this domain, the geometry of space itself loses its smooth certainty and becomes a probabilistic, fluctuating landscape. The nothingness we perceive is merely a large-scale average of this microscopic pandemonium. Theories attempting to tame this chaos propose that space is not continuous, but discrete. Loop quantum gravity, for instance, suggests that space is woven from tiny, finite loops, a fabric of interwoven threads where not even the vacuum is truly empty. Another approach, causal dynamical triangulations, models spacetime by building it from tiny, fundamental geometric blocks, like a cosmic mosaic. In both pictures, the smooth continuum of Einstein's universe emerges from a deeper, grainy reality, much like a digital photograph resolves into a clear image from countless tiny pixels. This fundamental graininess could have observable consequences. When gamma rays travel across billions of light-years from distant cosmic explosions, their journey through this spacetime foam might leave a subtle fingerprint. The foam could act like a fine cosmic mist, causing higher-energy photons to travel ever so slightly slower than their lower-energy counterparts. By searching for this delayed arrival in the light from gamma-ray bursts, astronomers are hunting for the texture of nothingness itself. The holographic principle finds a natural home here, as the information encoding our three-dimensional world could be a direct result of this foamy, informational substructure. The universe may fundamentally be a network of quantum relationships, with our reality and its vast emptiness projected from the frenetic interactions at the Planck scale. This vision of a granular void, seething with transient tunnels and holes, forces a profound realization. The majestic order of the cosmos, from the spiral arms of galaxies to the orbits of planets, ultimately rests upon a foundation of pure, random chaos. That quantum foam, seething with potential, might be the very womb of the cosmos. Our origin story begins not with a bang in a void, but with the birth of space and time from the vacuum itself. The Big Bang was not an explosion in space. It was the rapid emergence of spacetime from a profound quantum fluctuation. In this view, the universe literally popped into existence from nothing. A colossal realization of the quantum principle that something can come from nothing, so long as it balances out quickly. But how can a universe balance its books? Theories like the no-boundary proposal, developed by James Hartle and Stephen Hawking, offer a breathtaking answer. They suggested the early universe had no initial singularity, no point of infinite density and temperature. Instead, it arose smoothly from a Euclidean vacuum state, a realm where time as we know it did not yet exist. Hawking famously described this by saying the universe would be completely self-contained, neither created nor destroyed. It would just be. Imagine the history of the cosmos as a sphere. The Big Bang is not a point on the sphere, it is the South Pole. There is no edge there, no boundary, no before. The laws of physics hold everywhere. Another compelling model is the tunneling from nothing. Here, the universe quantum tunnels from a state of absolute nothingness, no space, no time, into a tiny, nascent cosmos. It is the ultimate quantum leap, bypassing the need for a creator or an initial cause. These ideas are not pure philosophy. They have a direct, observable consequence: the cosmic microwave background. The stunning uniformity of this ancient light, its near-perfect sameness in all directions, could stem from a primordial vacuum coherence. Before inflation, the entire observable universe was a single, connected quantum region, a patch of vacuum that shared the same properties throughout. Then inflation struck. This vacuum-like energy field, the inflaton, seized upon those tiny, innate quantum jitters in the void and stretched them to cosmic proportions. The microscopic seeds of structure, born from the vacuum's uncertainty, became the gravitational wells that would eventually pull in matter to form galaxies, stars, and planets. Every galaxy we see is a magnified quantum fluctuation, a fossilized ripple from the first moments of time. This Genesis story forces a profound question: can something truly come from nothing? The vacuum of quantum physics is not a philosophical nothing. It is a physical state brimming with potential, governed by laws. But if those laws themselves are part of the universe, how can they exist before it? The mystery echoes far beyond our laboratories, resonating with ancient traditions that have long contemplated the nature of emptiness. The stillness of a monk's meditation contains a universe of insight. For over 2 millennia, Eastern philosophies have contemplated a concept that physics is only now beginning to articulate: a profound understanding of emptiness known as Sunyata. In Mahayana Buddhism, Sunyata does not mean a barren void or mere nothingness. It describes a ground of being that is empty of independent, permanent existence, yet overflowing with potential and interconnectedness. The 2nd century philosopher Nagarjuna articulated this as the middle way, a path that avoids 2 extremes: the belief in eternal, unchanging substances and the belief in utter nihilism. He taught that because all things are empty of a separate self, they can arise dependently, woven into a seamless web of cause and condition. This is not a void of absence, but a fertile silence from which the symphony of form emerges. The parallels to our quantum vacuum are startling. Just as Sunyata is a fullness of potential, the quantum vacuum is the lowest energy state, yet it teems with virtual particles and fluctuating fields. A particle does not have a solid, independent reality. It is a temporary excitation of a field, an event dependent on the whole system. Both views dissolve the idea of isolated objects in a container of space, pointing toward a universe of dynamic, relational processes. This relational view finds another echo in the ancient Taoist concept of Wu, or non-being. In the Tao Te Ching, it is the emptiness within a pot that gives it utility, the space in a room that makes it habitable. Wu is the unnameable source from which all creativity springs, the quiet ground of being that allows for the 10,000 things to manifest. A beautiful metaphor for this interdependent emptiness is Indra's net. a cosmic web stretching to infinity. At every intersection of this net hangs a brilliant jewel, and each jewel perfectly reflects every other jewel in the entire cosmos. If one jewel is touched, the ripple echoes through the entire network. Every entity contains the image of the whole, and the whole is present in every part. This is not unlike the quantum entanglement that instantly links particles across vast distances, or the holographic principle suggesting that all information about a volume is encoded on its boundary. The universe begins to look less like a collection of things and more like a single, unfolding event. So, can this ancient wisdom inform our modern scientific inquiries? The philosophical depth of Sunyata challenges the substantialist view that reality is made of solid, independent building blocks. It encourages us to see nothingness not as an inert stage, but as a creative, dynamic ground from which all form arises. This shifts our very perception of the vacuum, framing it not as a passive background but as an active participant, a plenum of potential that might even be tapped. This vision of the void as a creative ground naturally leads to a tantalizing question. If the vacuum is this active, could we ever learn to draw power from its endless fluctuations? The dream of drawing limitless power from the void is a seductive one. Science fiction paints visions of civilizations harnessing the vacuum's infinite energy, but the scientific reality is a labyrinth of profound physical constraints. This concept, known as zero-point energy, refers to the baseline jitter of quantum fields that can never be switched off. The mathematics suggests every cubic centimeter of empty space contains more energy than all the matter in the known universe, a staggering potential that seems to promise a cosmic power source. Yet, this energy is fundamentally locked away by the very laws of physics that permit its existence. The central obstacle is thermodynamics. The vacuum is already in its lowest possible energy state, its ground state. To extract useful work from any system, you need a difference in energy, a gradient like hot and cold reservoirs in a heat engine. But the zero-point energy is uniform, a constant hum everywhere. There is no colder reservoir to dump heat into, no way to create a flow. Trying to harness it directly is like trying to power a ship by dipping a bucket into a perfectly still, sea-level ocean that stretches to infinity. Where does the current flow? Scientists have explored more nuanced possibilities, such as the dynamic Casimir effect. If you vibrate a mirror at nearly the speed of light in a vacuum, the theory suggests you could convert virtual photons into real, detectable light, essentially shaking energy loose from the void. While laboratory demonstrations using cleverly designed circuits have produced photons this way, the energy input required to move the mirror vastly exceeds the tiny trickle of energy extracted. It becomes a spectacularly inefficient demonstration, not a power plant. This connects to one of the most speculative yet captivating potential applications, the Alcubierre warp drive. Physicist Miguel Alcubierre proposed a mechanism for faster-than-light travel not by moving a ship through space, but by contracting spacetime in front of it and expanding spacetime behind it. The engine for this incredible feat would require a shell of exotic matter with negative energy density, a substance that could, in theory, be manufactured from the vacuum itself through sophisticated manipulations of quantum fields. This exotic matter would create a warp bubble, isolating the ship from the rest of the universe and allowing the fabric of space to do the moving. Yet, the energy requirements are astronomical, potentially needing the mass energy of entire stars, and the stability of such a bubble remains entirely unknown. So, are we forever barred from the vacuum's treasure trove? The laws of physics as we know them present a formidable cage. The dream of a zero-point energy device often stumbles into the realm of perpetual motion, a thermodynamic impossibility. The vacuum's energy is real and powerful, but it is a background actor, not a tap we can simply turn on. This forces a sobering ethical reflection. If such a power were ever conceivable, who would control it? The entity that could command the energy of emptiness itself would hold a key to the cosmos, with implications for energy, travel, and even warfare that are difficult to fully comprehend. The void offers profound gifts, from the mass of particles to the expansion of the universe, but its ultimate power source may be one secret it is destined to keep. That same quantum silence which gives us mass and structure could also be our undoing. The power to manipulate the vacuum carries a burden of cosmic responsibility, forcing us to ask if some doors are better left unopened. Philosophers like Nick Bostrom highlight a terrifying possibility known as vacuum decay. Our universe might not be in its true, lowest energy state. Instead, we could be living in a false vacuum, a temporarily stable bubble of spacetime, like a valley on a vast hillside. But somewhere out there, a deeper valley exists, the true vacuum. If a high-energy event, perhaps in a particle collider or a cosmic process, created a tiny bubble of this true vacuum, it could be catastrophic. This bubble would expand at the speed of light in all directions, its boundary rewriting the very laws of physics as it goes. Atoms would cease to hold together, forces would unravel, and the universe as we know it would be erased, replaced by a new reality utterly incompatible with our existence. There would be no warning, just an instantaneous end. This is not science fiction, but a stark implication of our best physical models. Ethicists invoke the precautionary principle, arguing that when an action could cause severe or irreversible harm, the burden of proof falls on those taking the action to show it is safe. But how can we prove a negative, that our experiments will not trigger such an event? This debate was not just theoretical during the planning of the Large Hadron Collider. Fears surfaced that its unprecedented energies could create microscopic black holes or other exotic states that might destroy the Earth. The scientific community addressed these concerns through rigorous calculation and open consensus, concluding that the risks were negligible, in part because cosmic rays with far greater energies naturally bombard our atmosphere without causing vacuum decay. Yet, the ethical framework for such decisions remains fragile, built on trust in expert opinion rather than any global governance for cosmic-scale experiments. As our technological reach extends, we must confront a profound question. Should humanity, in its thirst for knowledge, voluntarily limit its reach into the void? Is our curiosity worth a risk, however infinitesimal, that could end everything? This ethical dimension connects to an even more intimate mystery: the role that this active nothingness might play in our own consciousness and perception of reality. Your own mind is constantly shaping the empty space you perceive. When a meditator sits in silence, aiming for a state of pure awareness devoid of all thought and sensation, they are encountering a subjective void, an internal emptiness that feels vast and fundamental. This inner experience of nothingness bears a curious resemblance to the quantum vacuum, a plenum of potential from which all things can spring. It raises a profound question: could the mind and the void be deeply intertwined, two expressions of the same underlying reality? Some interpretations of quantum mechanics venture directly into this mysterious territory. The von Neumann-Wigner interpretation proposes that consciousness itself is the final agent that collapses the quantum wave function, transforming a haze of probabilities into a definite, observed reality. In this view, the act of observation is not a passive recording but an active participation in creation, potentially linking our conscious awareness directly to the behavior of the vacuum's fluctuating fields. The physicist Erwin Schrödinger, deeply influenced by Eastern philosophy, pondered this connection, wondering if the perceived world of separate objects, including the void between them, is ultimately a mental construct, a grand illusion crafted by our senses. Neuroscience confirms that our brains are not blank slates passively receiving information. They are active prediction engines, constantly filling in gaps. Look at the Cannes triangle. A simple image of three Pac-Man shapes arranged in a ring. Your brain instantly constructs the illusion of a bright white triangle superimposed on top, complete with defined edges, even though those edges are not physically drawn. The emptiness is perceived as a solid object. Your mind creates form from nothing, stitching together a coherent reality from fragmentary sensory clues. This constructive process extends to our most profound experiences. In deep meditation, under sensory deprivation, or with the use of psychoactive substances, people consistently report states of ego dissolution and a feeling of merging with a boundless, empty unity. This is not a perception of lack, but of a vibrant, interconnected plenum, a direct psychological parallel to the quantum plenum. Could it be that consciousness itself is not merely a product of the brain's neurons, but emerges from or interacts with the fundamental processes of the quantum vacuum? This is a highly speculative but captivating frontier, suggesting that the silent, observing self and the seething void of potential are not separate, but different facets of a single, incomprehensible whole. This introspective journey to understand nothingness has, for centuries, found its voice not in equations, but in art, where the void is given form and feeling. The deep, resonant blue of an Yves Klein painting does not feel like a mere color. It feels like a doorway into an infinite and sacred space, a visual echo of the cosmic void we have been exploring. This is not an empty blue, but a full one, charged with the same latent potential that physicists find in the quantum vacuum. Artists and writers have always been cartographers of nothingness, using their mediums to map the very territory science strives to quantify. The 18th century poet Basho captured this with stunning economy in his haiku. The old pond, a frog jumps in, sound of water. In that momentary silence before the splash, the poem holds the entire weight of the void, a stillness brimming with anticipation. This artistic exploration often strips away everything to reveal the power of what remains. The composer John Cage demonstrated this with his infamous piece, 4 minutes and 33 seconds, where the performer sits in silence. The music becomes the ambient sounds of the concert hall, the coughs and rustles and the listener's own heartbeat. Cage framed the silence not as an absence, but as a field of pure potential, a blank canvas upon which any sound could manifest. He once said that there is no such thing as silence, only unintended sounds. His work is a direct parallel to the quantum vacuum, a silence teeming with unseen activity. Similarly, the sculptures of Anish Kapoor, with their deep, dark voids and mirror-like surfaces that swallow light and reflection, create spaces that feel both infinite and intimate. They are not objects you look at, but portals you fall into. Science fiction uses the void to explore our deepest anxieties and wonders. The deep space sequences in the film 2001, A Space Odyssey, are not filled with laser battles and roaring engines. They are long, quiet, and majestic, emphasizing the sheer, overwhelming scale of the emptiness between worlds. This evokes the sublime, a feeling of terror and awe in the face of something vast and incomprehensible. Liu Cixin's novel The Three-Body Problem takes this further, grappling with the silence of the cosmos itself. The story revolves around the fear that the universe is a dark forest, where the vacuum between stars is not empty but hiding potential threats, making silence a survival strategy. These narratives transform the void from a passive backdrop into an active, almost sentient force. So, does art help us comprehend a concept as abstract as nothingness? It provides a bridge between the intellectual understanding of quantum fluctuations and the emotional, gut-level feeling of staring into the abyss. Art gives the void a texture, a color, and a sound. It allows us to feel the isolation and the infinity, to confront the terror and the creative potential that emptiness represents. When an artist describes the void as a space of pure possibility, they are speaking the same language as a physicist describing the latent energy of the vacuum. Both are pointing toward a fundamental truth, that what appears to be nothing is, in fact, the ground of all being. This creative impulse to fill the emptiness leads us to wonder if we are alone in doing so, and whether the cosmic vacuum might also be a cradle for life beyond our own world. This profound silence of the cosmos might be the vacuum's most telling message. We gaze out at a galaxy that should be buzzing with activity, filled with countless stars and potentially habitable worlds, yet we are met with an unnerving quiet, a great silence known as the Fermi Paradox. If the universe is so vast and old, where is everybody? The answer may lie not in the stars themselves, but in the properties of the emptiness between them. The vacuum is not a neutral backdrop for life, it is a gatekeeper. For complex life to arise and persist, the cosmos requires a breathtakingly precise balance, and the vacuum energy, the cosmological constant, is a master dial in this setup. If this energy were even slightly stronger, the universe would have expanded too rapidly after the Big Bang, preventing matter from clumping together to form galaxies and stars. No stars means no planets, and certainly no life. If it were slightly weaker, gravity would have pulled everything back into a catastrophic crunch long before life could evolve. We exist in a universe where this number is almost perfectly tuned to zero, a cosmic coincidence so unlikely it demands an explanation. This is the core of the rare Earth hypothesis, which argues that the combination of factors needed for a stable, life-bearing planet is extraordinarily uncommon, and the vacuum's specific properties are the first and most critical filter. Astrobiologists like Milan Cirkovic take this a step further, suggesting that the vacuum's instability might be the source of periodic cosmic catastrophes. A vacuum decay event in a distant galaxy, or a nearby gamma-ray burst triggered by exotic quantum phenomena, could sterilize vast regions of space, acting as a reset button that keeps the galactic choir silent. These are not one-time events, but recurring filters that may regularly prune the tree of life. We can frame this cosmic loneliness with the Drake equation, a formula that estimates the number of communicative civilizations in our galaxy. Several of its key terms are directly hostage to the void. The fraction of stars with planetary systems depends on the initial conditions set by the primordial vacuum. The number of planets that can support life is shaped by a stable cosmic environment, free from vacuum-driven annihilation events. And most hauntingly, the length of time such civilizations release detectable signals might be cut short by a vacuum catastrophe they never saw coming. The silence we perceive may not be a sign of absence, but a graveyard of civilizations that flashed into existence only to be erased by the indifferent physics of nothingness. This leads to a deeply personal reflection. Are we an incredibly early species, one of the first to arise in a galaxy that is only now becoming habitable? Or are we tragically late to the party, listening for echoes in a silence that follows a long, extinct chorus? This cosmic perspective forces a new urgency upon our own future. If the vacuum holds such destructive potential, our long-term survival may depend on becoming a multi-planet, and eventually a multi-stellar species. We would no longer be passive inhabitants of a single world, but active navigators of the void, learning to read its subtle threats, and perhaps one day learning to shield ourselves from its ultimate dangers. Our destiny may be to colonize the emptiness, not just to explore, but to ensure that the faint whisper of human consciousness is not so easily silenced by the cosmic dark. These colossal arcs would drift for centuries, their hulls a fragile barrier against the interstellar void. Inside, generations of people would live and die, their entire world contained within rotating habitats like O'Neill cylinders, which use centrifugal force to mimic gravity. These self-contained ecosystems would be the ultimate test of our ingenuity, requiring perfect closed-loop systems where every drop of water and molecule of air is constantly recycled. The vacuum outside is not just empty space to be crossed. It is a resource to be mined. Futurist Isaac Asimov once envisioned that overcoming the challenges of space would mark a necessary step in human maturity, a way to guarantee our survival against planetary catastrophes. This means learning to harness the void itself, perhaps by tapping into the quantum vacuum's zero-point energy for propulsion and power, turning the apparent nothingness into the fuel for our journey. Projects like Breakthrough Starshot are already taking the first small steps, planning to send tiny probes to nearby stars propelled not by rockets, but by the gentle, constant push of light sails. The engineering hurdles are almost beyond comprehension. Shielding the ship from cosmic radiation would require massive magnetic fields or layers of water ice, and sustaining a biosphere for hundreds of years demands a resilience we have never achieved. But beyond the physics lies a deeper, human challenge. A generation ship is a society in a bottle, hurtling through the dark. Over the centuries, its culture would drift, its language evolving, its original mission perhaps fading into myth. The descendants born aboard might have no memory of Earth, viewing their ancestral home as a distant legend. The ethical questions are profound. Do we have the right to commit countless unborn generations to this isolated voyage, with no choice in their destiny? If we could truly master the energy of the vacuum, making interstellar travel commonplace, what would become of humanity? We would transition from a species rooted to a single world to a civilization that lives within the void, building megastructures like Dyson spheres to capture a star's entire energy output. Our future may not be on planets, but in the space between them, in artificial worlds of our own creation. This forward-looking dream forces us to confront our role in the cosmos. Are we destined to be passive observers of the vacuum's grand story? Or will we become active participants, weaving our own narrative into the fabric of nothingness itself? The ultimate fate of the vacuum may be to become a home. That final, silent cosmos is the ultimate expression of the vacuum's power. Two starkly different endings await our universe, both dictated by the subtle properties of the void itself. The first is a slow, cold fading known as the heat death. In this scenario, the relentless acceleration driven by dark energy continues, pushing all other galaxies beyond our cosmic horizon. The night sky will go dark, star by star, as the universe expands into an ever colder, more dilute state. All energy will eventually even out, temperature differences will vanish, and no work will be possible anywhere. It is a state of maximum entropy, where the cosmos becomes a uniform, lukewarm sea of particles and radiation, unable to ever form a structure again. Time itself may lose all meaning as change becomes impossible. This is the vacuum as a frozen wasteland, a quiet, eternal stillness where the story of the cosmos simply stops. But there is a far more violent alternative, the Big Rip. If the repulsive force of dark energy is not constant but actually strengthens over time, its grip on the cosmos will tighten. First, it would tear apart galaxy clusters, then individual galaxies. As the acceleration becomes infinitely strong, it would rip stars from their solar systems and planets from their stars. In the final, terrifying moments, the fabric of spacetime itself would tear, pulling apart atoms, atomic nuclei, and even the fundamental particles that make up everything. The universe would end not with a whimper, but with a catastrophic shredding, leaving behind nothing but a vast, utterly featureless void. The difference between these fates hinges on a single number known as the equation of state, which describes the pressure dark energy exerts. A value of -1 suggests a steady cosmological constant, and leads to the heat death. A value more negative than -1 points toward the Big Rip. This is where powerful new tools like the James Webb Space Telescope come in. By observing the light from the most distant supernova and galaxies, it refines our measurements of how the universe's expansion has changed over billions of years, giving us a clearer reading on dark energy's true nature. Cosmologists like Lawrence Krauss have framed this as a cosmic choice written into the vacuum's energy. The void could be a patient, freezing blanket, or it could be an impatient, destructive force. These are not the only possibilities we have contemplated. For a time, the Big Crunch was a favored model, where the collective gravity of all matter would eventually halt and reverse the expansion, pulling everything back into a fiery singularity. There is a certain elegance to this cyclical idea, a universe that breathes in and out, perhaps giving rise to a new cosmos in each cycle. Yet our observations have ruled this out. The expansion is accelerating, not slowing. The vacuum's repulsive push has already won the battle against gravity's pull. So what meaning can we find in a cosmos destined for such emptiness? Whether frozen or torn, the final state is one of profound isolation and silence. It forces a deep reflection on the temporary, precious nature of structure and consciousness. We exist in a brief cosmic spring, a flourishing of complexity between the fiery dawn and the long, cold winter. Our story, and the story of everything we know, is written on a page that the vacuum will eventually reclaim. This brings our journey full circle, from the first philosophical questions about the void to its ultimate, chilling dominion over all of reality. Our entire journey through the void reveals a single, stunning truth. The emptiness is not a passive stage, but the most creative actor in the cosmic play. From the warped fabric of space-time to the seething quantum foam, from the explosive birth of inflation to the silent push of dark energy, we have seen that nothingness is the wellspring from which everything flows. This dynamic medium gifts particles their mass, dictates the arrow of time, and weaves the galactic web we call home. The ancient wisdom of Sunyata, the quantum puzzles of entanglement, and the artistic renderings of the sublime all point toward the same profound understanding. Emptiness is a fullness, a relational ground where existence and non-existence dance in an unending embrace. The key takeaway is not just a collection of facts, but a shift in perception. The solid world you touch, the vast spaces between stars, and the very flow of time are all magnificent illusions emerging from a deeper, vibrant nothing. This synthesis of science and philosophy invites a deeply personal reflection. If the void is so fundamental, then our own consciousness, our sense of self, is also interwoven with this foundational emptiness. We are not just observers of the cosmos, we are temporary expressions of its most basic ingredient. Every discovery about the nature of nothingness quietly reshapes our own identity, urging us to look with fresh eyes not only at the night sky, but at the quiet spaces between our own thoughts. As we stand at the edge of this understanding, the tapestry of the void is complete, yet it leaves us with one final, intimate question about our own place within its silent, generative heart. The quantum jitters of virtual particles and the vast cosmic acceleration are not separate phenomena. They are different verses in the same epic poem written by the void. This story beneath nothingness reveals that empty space is not a blank stage, but a rich, evolving character in the universe's own narrative. We have journeyed from ancient philosophical battles to the warped fabric of relativity, from the frantic quantum foam to the instantaneous links of entanglement. Each discovery peels back another layer, showing us a void that bestows mass upon particles, directs the relentless arrow of time, and carved the cosmic conditions that allowed for life itself. This silent partner is the canvas upon which every galaxy, star, and thought is painted. So the next time you gaze into the night sky or simply sit in a quiet room, let this new vision settle in. See the void not as a mere emptiness to be filled, but as a vibrant canvas of infinite potential, a ground of being where every apparent nothing holds the latent seed of everything. How has this journey changed your perception of the space around you? Share your reflections in the comments below. And if you are eager to continue exploring the cosmos's deepest mysteries, be sure to subscribe. Thank you for venturing into the true nature of empty